Hi, I'm going to introduce you to calculating a 95% confidence interval using z-scores. Now we'll need to do this when we want to know what the population mean is for something, but in order to do this using z-scores, we're going to imagine that we still somehow know the population standard deviation. Now, up till now, we've been doing calculations with z where we were required to know the population mean value and standard deviation. And so right now we're going to kind of pretend that we don't know this value, but we do somehow still know the population standard deviation. Now, that is, just to refresh your memory, that is a little, it's a very artificial situation, because in order to calculate the population standard deviation, you might recall that we would do that by taking the square root of the sum of each score minus the population mean. And so if we don't know the population mean, it would be kind of hard or impossible to calculate this. And we square those and we divide by n. So that was our formula for calculating the standard deviation of the population. But bear with me, we're going to imagine that we do somehow know this guy. But this is something that's missing. So that's what we're interested in knowing, what the population mean is. Now, a mere mortal might go out there and get a sample of a particular size, so long as it's big enough, whatever big enough means. And maybe a good starting point would be, so that this is, equal to or greater than about 30 cases, or 30 individuals, or 30 in your sample size. Okay? And a mere mortal might go out and get a good, nice random sample of about that size and calculate the sample's mean. We'll call it x bar, right? When it's a sample, when it's a population, we use the Greek letter mu, and for a sample we use x bar. And so our best guess for a mere mortal might be that the population mean is equal to our sample's mean, and go home and call it a day. Good enough for us, okay? But we're no longer mere mortals here. We're on our way to becoming superheroes, and we recognize that that a sample is always going to be flawed. It's not the population. It's imperfect. And so we're nervous about this relationship. We're nervous and estimate, no matter how good and random our sample is and how big it is, we're worried that it's not a perfect, estimate of the population mean. So what we want to do is we want to create an interval. We want to create a window. So that, at the end of the day, we want to be able to say, well, maybe the population mean is equal to this best guess, but it might be a little bit more and a little bit less. So we're going to add some degree of, we'll call it error. Okay? So our best guess will be that the population mean is equal to our sample plus and minus some degree of error. Now, how much error to add and subtract is going to be determined by the size of the degree of confidence that we're going to have here. So as I told you, I wanted to talk about doing 95% confidence intervals. So to be 95% confident that the interval containing the true population mean is my sample's mean plus and minus some error, whatever I plug in here for this, percentage, the size percent I want to do, is going to wind up determining how big my error should be. All right, so let me spell that out a little bit further here. So this is going to wind up being, again, the best guess is the sample mean plus and minus the error. So what is the error made up of? Right? The error is going to be made up in this case of a z-score. The z-score is going to be determined by that the degree of confidence that we want to have. And we'll multiply that by an error term, which will use the standard error of the mean. Okay? All right, so there we have our formula here. So at the end of the calculation, I'm going to want to be able to say something like, hey, I'm 95% confident that the interval containing this true population mean is somewhere between my sample's mean plus and minus this many standard errors. let's try it out. So let's say that we have sampled 36 individuals. Let's use IQ as an example. We've been doing a lot of problems with IQs. And so once again, we do know that the population mean is 100, but we're going to pretend that we don't know that, okay? And we know that the population standard deviation for IQ is 15, all right? And so we've gathered 36 people randomly and administered an IQ test to them. And let's say that our sample mean is 104.5. Now again, let's imagine that this was 36 randomly selected people from the population, and the population mean is known to be 100. So our best guess would have been that, hey, 36 people ought to have a mean pretty close to 100. Okay, and so we're already like, this is interesting. This group had a mean of 104.5. All right, so let's build this confidence interval around this thing. Okay, so we're going to add and subtract some amount of error here. Now, for a 95% confidence interval, again, if you want to visualize this, we're going to try to guess what this population mean value is, but we're going to try to build a window around it so that this represents 95%, okay? And therefore, we have 2.5% that'll fall above it, and 2.5% that will fall below this point. Now, if we look in our z-score table, and I'm going to recognize that, hey, these two pieces here represent column C in most standard z-score tables. And most z-scores tables report things as proportions. So my proportion in this C piece on each side, it's symmetrical, is equal to a p-value of 2.5% is equal to 0.0250. Okay, so if I look in column C for 0.0250, I find a z-score here equal to 1.96, positive on this side and 1.96 negative on this side, okay? So that is the corresponding, that's where I get this for a 95% confidence interval. I'm always going to be using this value of 1.96. And so you can, as you're proceeding here, you can just remember that for a 95% confidence interval using Z, the z-score is always going to be 1.96. But hopefully this explains, the magical reason why I am using 1.96. It's the score around, it's the z-score that cuts off an inner 95%, exactly precisely 95% of a total 100% normally distributed population. Okay. All right. So the last item that I need is my standard error. Now, maybe out to the side, I'm going to calculate what my standard error is equal to. So remember, the formula for standard error is equal to the population standard deviation divided by the square root of whatever sample size we're using. Okay, so being an IQ problem, I remember that the population standard deviation is 15, and my sample size is 36. So I'm taking the square root of 36. All right. That is 15 divided by the square root of 36 is 6, right? So I'm going to calculate 15 divided by 6 is 2.5. Okay, this equals 2.50 is my standard error. All right, I'll just simply plug that in over here, 2.50. Okay, let's calculate this error term then. My error term is going to be 1.96 z's, or just about 2 standard errors. So again, I'm going to have 104.5 plus and minus. Let's calculate what 1.96 times 5 is. Let's multiply that by 1.96, and that's 4.90. Okay, now we're going to add and subtract that. And so the lower limit of this window is going to be 104.5 minus 4.9 is 99.62 104.5, whoops, 104.5 plus 4.9. I did that wrong. Slow down. 104.5 plus 4.9 is 109.4. And there we have it. That is the window around which I'm 95% confident that the true population mean lies. Now let's put that into a meaningful sentence here. I'm going to go back to how I wrote my formula for this, and I'm just going to put add the words I am to the front of it. So I'll say I am 95% confident that the interval containing the true population mean IQ is somewhere between 99.6 and 109.4. Now let's reflect on what that tells me about this sample of 36. I now suddenly do remember, we were pretending that we forgot what the population mean IQ is, that it's 100, and I suddenly remember, oh yeah, the population mean is indeed 100. 100, as you can see, does indeed fall within this range here. So I can kind of backwardly talk about my sample of 36 people and recognize that they're quote-unquote fairly normal. All right, using them, I predict that the population mean IQ is somewhere between 99.6 and 109.4, and it does indeed capture 100, just barely. It's a little high, right? Again, I would have normally been expecting these people, if they were truly random and nothing unusual had happened to them or been done to them, that they should have a sample mean of about 100, but instead I saw a mean that was a little on the high end, but it is not so high as to be considered, highly unusual. The true population mean does land within this interval. So this is one way that we can use 95% confidence intervals to sort of tell us about the samples, okay?